If my voice seems sped up about 10% or so on this video, or if my pen seems to be darting about pretty rapidly, then just adjust the speed, the playback speed under the settings menu. A lot of my videos are sped up after being posted. That's better than all of my videos being deleted, because that's what happened in the past. That's why this channel is called Winter's Ghost. It was Winter Snow, but after so many videos were deleted, it was a ghost of a channel. At times I also have to use the slow cell phone towers to upload my videos, because if I use the internet, then they'll be uploaded with very low resolution at certain times. So this channel is, for the most part, just a sequence of disasters, and that's why I do really low quality, no effort videos, because there's no reason to put any effort into a disaster channel. Here's a two-boat calculus problem. I heard about this years ago on YouTube, and no information was given on it. It's just the basic logic that's used whenever you have two modes of transportation. In this case, you got a fast motorboat that can go infinite speed, and behind it, it's pulling a rowboat. So the situation is, this boat's in a race. The person driving this motorboat, they got to get from start to finish as fast as possible. The boat can go infinite speed, but the faster it goes, the sooner it runs out of fuel, because it encounters drag. So if you make the motorboat go infinitely fast, it'll stop immediately and run out of fuel. Then you have to row the whole way. It only has enough fuel to go 10 kilometers per hour the entire distance, and then it'll run out of fuel at the very end. But it actually wants to go faster than that, and so it's pulling the rowboat, so it needs to go as fast as possible until it runs out of fuel, and then the guy rows the rest of the way. So in regards to just having two modes of transportation, this actually applies if you're running a long race, such as a marathon. You can't just start sprinting. You have to pace yourself and run at an ideal speed before, the faster you run, then the sooner you finish the race. But if you run too fast, you end up having to walk, and it slows you down. If you have, say, a car and with a bike on the back, the car encounters drag and runs out of gas, then you have to ride the bike, or you could do car and walking, whatever. Two-stage rocket, possibly. This isn't my field, but it's logical to think that rocket fuel has to be designed in a certain way to give that rocket a certain velocity. If the rocket fuel burns too fast, then you're just looking at gunpowder, and it'll just explode and shoot off immediately. The rocket will go really fast, but encounters so much drag, it doesn't get very far. And so also too, I was thinking about three modes of transportation, say car, and then you run, and then you walk. I don't know if that's where multivariable calc comes in. I haven't had that class, but I figure there's probably some way to solve that. So here's the situation. The distance is 10 kilometers on the race. The velocity of the motorboat, V sub n, can go from 0 to infinity in speed. Velocity of the motorboat, if it does go just a maximum of 10 kilometers per hour, let's see, 10 kilometers per hour to go 10 kilometers, it'll run out of fuel at exactly the finish line. That's the important part. So if it just goes exactly 10 kilometers per hour, then it'll run out of fuel right at the finish line. Here's the conversion equation. 10 kilometers is the distance, 10 kilometers per hour, they cancel. That means it'll take 1 hour to go exactly 10 kilometers. Velocity of the rowboat is also 10 kilometers per hour. So it's the same as that boat if the boat wants to go the whole race and not run out of fuel. So yeah, obviously none of this is my field. I just wanted to come up with a logical equation and a logical way to put some equations together to come up with a graph that actually makes sense. Velocity of the motorboat is here. You can increase it on up to infinity. Here's the time you finish the race. As that velocity of the motorboat gets faster and faster, your time gets lower and lower until you get to a certain point, the nadir right here, and then it starts to creep up and right here and run right along that line. Here's where we use the derivative of our equation. The derivative just gives us the slope of our line. We take the derivative and set it equal to 0 because we want slope, also known as m, to equal 0, which just means it's a horizontal line, not going down and not going up. your slope is negative. Once it reaches 0, then it starts to go back up, which means you increase your time. So we take the derivative, set it equal to 0, and that gives us the lowest point on our graph. I already did a couple of videos explaining derivatives, and I try to do them in a way so that somebody with just basic math skills could understand them. So see those videos if you're interested. What's interesting about this graph is it's super logical. So if the velocity of the motorboat is infinity, then you're going to finish the race in exactly 1 hour, which is how long it takes just to row the entire way. Because if you try to go infinitely fast in the motorboat, you immediately run out of fuel and you have to row the entire way. So what I think is interesting is just to be able to use simple logic to put equations together to come up with a graph that looks just like this, that totally makes sense on how you want your motorboat to go a certain speed to finish as fast as possible. And if you go faster than that, you'll end up just coming out with the time that it takes to row the entire way. So now here's what's fun here with this logic exercise, just coming up with a toy equation, meaning an equation that's not really used in real life, but it does give logical answers. So here's the logic part, the velocity distance relationship. Increase your velocity, you'll increase your drag, and thus you decrease your distance. Distance of the motorboat is inversely proportional to the velocity of the motorboat. That's proportional right there. So increase the velocity of your motorboat, you'll decrease your distance. Force of the drag is also proportional to velocity squared. This is from the drag equation. Let's do some more logic exercises. Fuel will be proportional to the distance of the boat. The more fuel you have in your motorboat, the farther you go. So let's do an inversely proportional thing here. Distance of the motorboat, make that a little bit better of an M there. There you go. It's going to be proportional to your fuel, and then inversely proportional to V squared, because that's your drag. If you want to add some complications and get technical about it, you could add something such as the average fuel weight of your boat. So if you have a lot of fuel that weighs a lot, divided by the volume of your boat. So if you have a huge volume and very low fuel weight, this won't matter, it'll approach 0. But if you have a huge fuel weight and a low volume of your boat, the boat will sink way down and it'll make you go a lot slower. So just something you could throw in for complication, but I'm not doing that here. So distance of the motorboat is equal to the fuel over velocity squared. Let's take the distance of the race course, since that's what we have here. I've learned from experience I need to write larger here because sometimes this stuff doesn't show up on the internet when I post it. Anyways, 10 kilometers is the distance of the course, equals fuel over 10 kilometers per hour squared. This is where I can come up with some real numbers. The boat needs to go this speed right here to finish the whole race and run out of fuel at the very end. I mentioned that at the beginning of the video. So 10 squared times 10 equals 1,000. So let's plug in 1,000 for the fuel right here. If you wanted to, you could just leave it as F or leave it as 1. It's all a toy equation, so it doesn't matter. At any rate, now we have the distance of our motorboat, 1,000 over V squared of velocity squared of the motorboat. Okay, distance over velocity equals your time. So take this whole distance, put it over time right here. Actually distance over velocity equals time. And what do we have here? Okay, so here's the distance of the motorboat, and then here's the velocity of the motorboat right here. And that'll give us the time of the motorboat. So it's 1,000 over V cubed. Now we have the time of our motorboat. Distance motorboat, time of motorboat, draw a box around them, and put a star next to them because they're important, and I'll use them later. Now let's do the distance of the rowboat. Distance of the rowboat plus the distance of the motorboat gives you your total distance. Total distance will equal 10 kilometers. There's the distance of our rowboat, which will be, actually take the 10 kilometers minus the distance of the motorboat. That's what I did right here, and that gives us the distance of the rowboat. Star it, draw a box around it because I'll use it later. Distance over velocity is time. Take the distance of the rowboat, and that's not a very good R there, over the velocity of the rowboat to get the time. Take our distance, divide it by the velocity, and there we go, and that gives us the time of the rowboat. The key for this is I'm using the distance of the motorboat as my common formula to plug into everything else. I use distance motorboat here, distance of motorboat right here. When I tried to come up with my time of the rowboat, at one point I tried to just do time motor plus time row gives total time. But I haven't defined my time of rowboat as it relates to the distance of the motorboat, because this is the common linking equation that links everything else together. But now that I've defined everything in terms of the distance of the motorboat, now I can use the equation right over here. Next up, time of the motorboat plus time of the rowboat equals your total time. And I've already derived all these equations. So here's time of motor, here's time of row, total time right there. Divide 10 into here, 10 into there, you get this. And simplify it down here. Actually take your v cubed, turn it into v to the negative third. And here's your total equation right here. And so what you want to do is take the derivative of that to find out where your slope is 0. I've already done a couple of videos on calculus to explain that. If you want to genericize this equation, it's fuel over velocity of motorboat cubed plus distance, the total distance over velocity of rowboat minus the fuel over velocity of rowboat times velocity of motorboat squared. And that will give you your total time. By the way, I just do this stuff for fun, as I've probably mentioned several times in my videos. And so a lot of times when I'm doing this, sometimes I'll be way out of practice. And for example, instead of just turning this velocity into a negative exponent, I went through the whole, the quotient rule, low d high minus high d low, and square the bottom, and away we go. So I did this the long way last time and got the same answer, but yeah, I was just way out of practice on calculus. That's kind of why I do this stuff. It gives me a way to practice it. So let's test our equation here and see if things somewhat work. Take the limit as the velocity of the motorboat goes to infinity. Take the limit of this whole thing here. There's velocity of motorboat, velocity of motorboat. That means this will approach 0, that approaches 0, and you end up with just the distance over the velocity of your rowboat. 10 kilometers right here over the velocity of the rowboat. So it gives you the total distance over the velocity of rowboat. So what this means is you row the entire time, because if you go infinitely fast in your motorboat, you immediately run out of fuel. Kind of like if you have an uncontrolled gunpowder explosion, instead of a nice steady rocket fuel burn, your rocket just blows up and you go no distance. So I just said right here, distance total over velocity of the rowboat gives you the time. Just distance over velocity equals time. Same thing as distance over time equals velocity. Now let's take the derivative of this whole thing here, d over dt of this whole thing, set our slope equal to 0. And I'll show how that works here on the next page. Set the slope equal to 0, take the derivative of it, go through the basic calculus. You get a velocity of the motorboat equals 15. And by the way, what I did on the next page, all I did is just changed around the velocity of the rowboat to see what would happen. Like I made the rowboat go 1 kilometer per hour, and then 5, and then 10, and 50, or whatever, because we only have 2 variables here, velocity motor and velocity of row. So basically just, you can change this around the velocity of your rowboat to get different results. It's kind of interesting, I think. Also, I should probably mention the reason I'm doing this video is because while I saw this problem mentioned on the internet, I actually never saw anybody do it. So that's why I'm doing this low budget version. So anyways, let's take the velocity of the rowboat equals 1. This is what the graph looks like. As the velocity of the motorboat increases, your time will decrease, of course, but then it gets down to the negatives. So you end up with an x and a y-axis, velocity of motorboat, and this is your time. So if the velocity of your motorboat is just 1.5 kilometers per hour, you actually go backwards in time to negative 138 hours. So that doesn't make sense. Let's increase the velocity of the rowboat to 3, see what happens. Turns out as you increase that velocity of your rowboat, you raise up that peak and you smooth it out, and it looks more like this. Now we end up with 4.5. Velocity of motorboat and your time. You go up 4.5 kilometers per hour, you finish in 4.5 hours, but that doesn't make sense because we already know the motorboat can go 10 kilometers per hour. So again, this is just velocity motorboat going to infinity. There's your time going down, and as expected, it dips down and then comes back up like it's supposed to. Also, what's fun about this simply plug in your equation to a graphing calculator. It'll give you these graphs. I didn't have to do any work on this other than just plugging the equation in. And I put my finger on the little line there, and it'll tell me what the low point is there, where the slope will equal 0. Because as I previously mentioned, that's where we want that's the point we're interested in right there. The slope's negative, reaches 0, and then goes up to positive. So we want that lowest point where slope equals 0. The graphing calculator does all the work for you. It only makes sense to increase the velocity of our motorboat when the velocity of the rowboat is 6.7 or greater. Actually, I need to do this. Greater than or equal to 6.7. And then what we got here, if the velocity of the rowboat equals that, plug in your numbers, we get velocity of motorboat 10.05, and your time is 0.99996. So now we're actually getting there in less than 1 hour. Okay, so the equation, as I had it listed, velocity of rowboat's 10 kilometers per hour. Here's your number, 15 and 0.85. So this is where the slope equals 0. The slope is negative, going down and down. Then the slope equals 0 right here, and then starts to go back up. So we take the derivative and set it to 0 to get that slope right here where slope equals 0. That means the boat, our motorboat, needs to go 15 kilometers per hour. We will finish in 0.85 hours. If you want to play around with some numbers, if you take the velocity of your rowboat and make it 20, that means your motorboat can go 30. You'll finish in that time. Velocity of your rowboat's 50. Velocity of your motorboat would be 75, and you finish in that time. And then from here on out, it's just plug and chug. I just took my answers to get my other distances. Here I got the distance of the motorboat by plugging in the formulas I already derived. Distance of motorboat right there, distance of rowboat right there. Distance over velocity equals the time. So now I got the time of the motorboat, then I get the time of the rowboat right there. So that's pretty much it.